Now, uh, in the morning, I have told you that the perplex can be done by or through the program which is known as build. I have told you that perplex can make the compositional analysis of an assemblage, particular pressure language, how it can be adjusted, as well as you were watching this, there is a file which is this showing the appetite balancing. Now, why is this used for before the perplex calculation? Now, whenever we get some analytical data from bulk rock analysis like XRF or something like that, what we get is an idea that how much of the compositions can be adjusted with phosphorus pentoxide present in the system. However, in perplex calculations, the phosphorus pentoxide, or rather I should say the apatite, which takes part in the reaction or not, they cannot be taken into account. And that is the reason we have to subtract an amount of calcium oxide from the system that can be balanced, or that can be balanced as we try to find out how much of the calcium oxide could have been subtracted should the P2O5 component enter the apatite structure. So this is a normal process or standard process to subtract the amount of the calcium oxide that is caused by the P2O5 or apatite in the system or Whitlockite in the system. However, this is not needed for softwares like, as an example, MELS. It was run by Georg. And in case of fractional crystallizations, they can show you the composition of the Whitlockite or apatite which are crystallized during a fractional crystallization process. Now, taking into account all of the other factors, if you want to see that how much of ferric could have been present in the system, you will have to go for molar calculation of oxygen by the FeO present, and from the FeO present, from the minerals, whether the ilmenite or hematite is present, if you are lucky enough to get equilibria, and then from there you can get the percentage of the oxygen in that system. However, those are complicated tasks, but apatite you can subtract for the apatite or the calcium oxide, which can be balanced for the apatite in a very normal basis. Now let's start with the build again, and let's see how can it be used to build a Schreinemaker diagram. Now the project name I am giving, that is CHREIN, Schreinemakers. The definition file will be normal, that is Holland Powell 02 dataset. The computational option file name, that will be as same as in case we have used for the pseudo section modeling or fractionation calculation. The current database components are these, and whether you want to or not, you can transform them or not. Saturated fluid, no. Saturated component, no, because you don't know use chemical potential activities and Kubernetes activity variables will also be no. That will also be no. Thermodynamic components from the set as we have entered previously, we can also enter it in this case or in this scenario also. Suppose I am taking sodium, calcium, potassium, magnesium, iron, silica and aluminum oxide. And to be to get this system or this situation less complicated, I am extracting or subtracting water, and let's see in an analogous situation what could be the convex minimization or hull minimization can show. Now there are three probabilities here. The three operations you can do. One is composition diagram, one is mixed variable diagram, one is section Schreinemaker's diagram. And I am going for the option 2. X-axis variable, which will be that is 2. Minimum values for temperature. Again, I am trying to get this. Minimum and maximum values of pressure will be 6,000 to 10,000 bar. Output a print file. I want a print file. I don't want to exclude those in member phases at all. Solution models, I am leaving them. Calculation title, calculate. And now we can see if we run the vertex from this, we can have a good idea shine. And then it again runs and it just finishes in a moment. Okay. And now if in the previous case we had to do the psect run, and in this case we will make a PSV draw run. And we don't want to modify the default plot, and we can observe that there is also a diagram which will be made by this operation, like the previous one that was section, pseudo sectional diagram which was made. And this is the diagram, and that will be the result. And notice that this diagram, it just has some lines, that is univariate line, and there are bivariate fields. Now interesting is that the thermocalc can also calculate these types of diagrams. In case of a thermocalc, on the contrary, you can give specific composition in the while doing the Schreinemaker's grid, and you can also, or you might also be able to see the activity correlations of the left hand side and right hand sides of the line. That is, whether it is accelerated or what should be activity of element in the particular line, the composition, and those can be output by giving the composition. And I think that Perplex doesn't give you that advantage. That's why in the next lecture I will try to show you that how thermocalc can be used to give you some definite compositional aspects on the lines. Now, for the previous day, we have seen or heard some equations or regarding some equations from the book of Philpotts and Foggy, and you will now see the exact regions from where these are found. But before that, I would like to show you something that is, or that can be seen now, as an example, there are different chapters in this book. You will be able to find out that where the CO2 and H2O, the system which are playing some role in this. Suppose this was the vein-like structures. This is a vein-like structure that can be, or that can actually, that was actually taken from the region or from the vein-like structure of the occurrence, and this is how fluid fluxes along the gradients of metamorphic temperature and pressure can generate different types of veins as well as different types of mineralogical association. And that was the thing I was talking about yesterday, that is how much of crystallization should happen or how much of mass can be balanced. There. Can I see it? Can you guys see it? No, okay. I think the black window should have been right for the observation purpose. Yes, you can see it actually. There will be chapter 21 and there is another chapter which is chapter 20, that is the flow and of the fluids along the gradients. Now, coming back to the system, that coming back to the topic, the coming back to the discussion, the topic of discussion today, that is somehow related to the geophysical laws, which on the other hand, or which on the additionally can take you different outlooks. Suppose that we are considering a system of the mantle where we want to know the cause of the plate tectonics, as well as we want to understand how the mechanism operates, as an example of the convection. Now, regarding the Rayleigh number, which can impose or which can show us how a convection cell or how a convection should take place, there are different types of things that we can do. Now, plate tectonics is a result of the mantle convection according to school of study, and the mantle convection is a result of crustal plate movement, which also can be shown by other studies. Now, for that purpose, we'll have to know the fluid dynamic processes, and this happens in a layer of the fluid heated from below and is marked by appearance of hexagonal cells of the liquid and rises from the bottom of the layer to the center and falls near the wall of the cell. And now we are going to build up some equation from that to see how this situation can take place. And we consider a rectangular controlled volume with the dimension of del x and del y, that is one dimension is del x, one dimension is del y. The flow rate per unit area in x direction at x is u, that is in the direction of x, and y. The flow that is happening, the velocity is u, and the flow rate per unit area is u plus del y by del x into del x minus of u, that is del y into del x minus of u, that is getting subtracted. And similarly, flowing the y direction should be del v into del y by del y. Okay, because del x and del y is the area to which the fluid flow is happening. And to find the next rate at which the fluid flow out of the set rectangular region shown in the given figure, we must combine the flow into D. And here we can see that del u del x plus del v del y will be the net outward flow in x direction is del v del y into dy. Net outward flow along the x direction will be u or del u del x into del y. Settle. Because the x and x will be cross-cutting each other, x and x along x direction, and you have to take this. Similarly, the net outward flow in x direction will be del v del y into del x, and the total amount of the rate of flow will be del u del x plus del u del x plus del v del y. And considering that there is no density variation, the del u del x plus del v del y will be 0. Okay. And from the equation of fluid dynamics, one thing we can say is that the rate of change of temperature with respect to time K by rho Cp, that is kappa, into del 2t del x square plus del 2t del y square minus u of x del t del x minus u of y into del t del y. And this actually comes from the equation of the force balance. I hope you can see. We find out.